This is lesson 6.4, reaction mechanisms. So the reaction mechanism is just the sequence of steps in a reaction. And each step is called an elementary step. So elementary steps are the individual steps in a reaction mechanism. You cannot observe these steps. Okay, they happen too quickly and they're at the molecular level. Intermediates are the product of a single step in the mechanism that are used in a subsequent step. They are not final products and they are not reactants. When you add the steps of a reaction together, the intermediates must cancel out. The molecularity of a reaction is an elementary step to indicate the number of reactants involved. So for example, unimolecular means that it's an elementary reaction that involves one single reactant particle. Bimolecular means that two reactant particles are hitting each other. And termolecular would be three reactant particles. However, these are really rare because in order to hit with enough activation energy and the correct orientation so that everything comes together in the same place and time is extremely rare. The rate determining step is the slowest step in a sequence. The slowest step is the one that determines the rate of a reaction. So, the rate expression for an overall reaction. The concentration of the reactants in the rate determining step has to appear in the rate expression or the rate law, and its order is equal to the coefficients. This is only for elementary steps, not for the overall reaction. So, for elementary steps, A going to be to products. This is unimolecular. There's only one molecule involved, so the rate would be equal to K times the concentration of A. The coefficient is just 1. 2A going to products means there's two molecules involved, so it's bimolecular, and the rate is equal to K times A squared, because the coefficient is 2. And the last one, A plus B going to products, is also bimolecular, and the rate would be equal to K times A times B. Now remember, this is only for each step of the reaction, not for the overall reaction. For the overall reaction, remember, you can't use the coefficients. So, when the rate determining step is the first step, the rate law is the same as the rate expression for the overall reaction. So here's an example. This is a two-step reaction. NO2Cl goes to NO2 plus Cl gas. This is a slow step. It's the rate determining step. In the next step, the NO2Cl gas, another molecule comes in and reacts with Cl to form NO2 plus Cl2. This step is very fast, and you can see here that chlorine is our intermediate because it's made here, but it's used up in the second step. So it cancels out. So overall, the reaction is two molecules of NO2Cl goes to 2 NO2 because we can add these two together, and chlorine gas. Now, the rate law is always found from the rate determining step because that's the slow step. It determines how fast the reaction is going to go. So because the first step is the slow step, rate is just equal to a constant K times NO2Cl, and there's only one, so the exponent is 1. Now, things get more complicated when the rate determining step is not the first step. So let's look at an example. In this reaction, step 1 shows that two molecules of NO combine to make N2O2. This is very fast. Then the N2O2 intermediate is used up when oxygen is combined to make 2 NO2. So the overall reaction, and this is the slow step, step 2, is 2 NO plus O2 goes to 2 NO2. Remember, the N2O2 is the intermediate, so it cancels out. So, ordinarily, the rate determining step here would be used to write the rate law. So rate would be equal to K times N2O2 times O2. However, N2O2 is an intermediate, and intermediates can never appear in the rate law. But N2O2 is formed in the first step. So the rate of formation of this would be rate equals K times NO squared, because there's two of them. So if we combine these, if we substitute in the rate law for the intermediate, we get rate equals K times NO squared times the O2. And that is the rate law for this reaction.